So in this video, we're going to begin our graphical analysis of motion. Our graphical analysis of motion. And what I want to do right away is I want to take a look at this graph pictured right here that I have inserted for you guys. I'm going to get rid of this title because I'm going to title this video a little differently. Oh no, it went away. Alright, my bad. We've got the position versus time graph back. And actually, that's what I was going to talk about. I was going to say we should take a look at this graph. And, well, what's this graph telling us? So we notice that on the x-axis, on our independent variable axis, we have time. And if we go ahead and jump over to our y-axis, we notice we have position in centimeters. All right, this is interesting. And we notice that it's comparing position and time. These are the two variables that are being compared. So quite naturally, we call this graph in physics, we call this the position versus time graph. So this is a position versus time graph. And in this video, we're going to learn about the position versus time graph, how to read the position versus time graph, and some interesting facts about the position versus time graph. So let's go ahead and get started. I have a bit more of a description of what's going on in this graph. Let me get it in view. So, okay, let's take a look here. So we got the preceding position versus time graph represents the cart on a track. So it represents some cart on a track. The motion detector is located at position x equals 0. And the positive direction, so we should keep this in mind, the positive direction is to the left. And I want to make sure we can still see that word. The positive direction is to the left. Now that's all I've included for questions right now. And that's all the kind of context that there is to this problem that I want right now. And I'm going to kind of make up the problem as we go so that we can discover the different various things about this graph. So the first thing I want to talk about is that what is the position, and actually I guess I'll write this down. Give me a second. So initially I want to know what the position of the cart is at time t equals 2 seconds. Well, that's pretty simple to figure out. All we gotta do is we gotta look at this graph. We've got to find 2 seconds on the x-axis. It is right here. And we, just like a normal graph, we go up to where we go up to the graph. That point is on the graph. We notice that point is right there at the 10 centimeter mark. We're looking for the position of the cart, and we note that the position is 10 centimeters. Now here's the question. Is it positive or is it negative 10 centimeters? The answer is positive. Let's go ahead and look at the question and figure out why. The reason it's positive is because, well, obviously, I mean, I guess it's kind of obvious. This is 10 right here. It's above the x-axis, therefore it must be positive. But if we were to draw this on a line, if we were to take a line, draw a line, and say that this was the motion detector right here at, oh, I guess it's 0 centimeters, excuse me, at 0 centimeters, where would we put the location of this, where would we put the location of the cart? Well, we would actually put the location of the cart right here. This green dot is the location of the cart. But why? Normally, we just said it was positive 10 centimeters. Why is it not right here, where it positive should be? Well, remember, in the problem, it said that the positive direction is to the left. So if it's 10 centimeters, it's always, the positive direction is always to the left, so it's the position of this cart is 10 centimeters to the left of the motion detector. So that is the position of the cart right here. If we look at it on a number line, that is the position of the cart at time t equals 2 seconds. That's pretty simple enough. Now, the next thing I want to know is what the velocity of the cart is at time t equals 2 seconds. And you're probably thinking, oh, this is not good at all. So I want to know the velocity this time at time t equals 2 seconds. And you're probably thinking, oh no, how am I ever going to figure this out? Because if you look at the graph, you notice that all you think you know is position and time. All this is very confusing. How are we going to find the velocity, which is the displacement per time? And this is where I'm going to say, hey, calm down. I want to notice something. So if we were to find here's what I propose. We're used to in math when we look at graphs, we're used to the idea of slope. And what is slope? Well, the equation for slope is the change in the y-coordinate divided by the change in the x-coordinate, which means it's the second y-coordinate minus first y-coordinate over the second x-coordinate minus the first x-coordinate. But looking at this graph, I noticed that the two y-coordinates are two different positions. So let me write that down. The two y-coordinates, I'll write this in the color that I have them underlined, they're just two different positions. So we've got the difference between two positions, and we're dividing it by, well, we notice that there's time for the x variables. So we're dividing it by a change in time. So we're dividing by the difference between two time intervals. And, well, if we take a look, we notice that, well, if we're finding the difference between two positions, well, that's just a displacement. So we can replace that with the displacement. And subtraction of 2 times, that's change in time. So we find out, well, change in displacement, so now we've got this neat equation that the slope is equal to the change in is equal to the displacement per time. And displacement per time, that is velocity. So the slope of a position versus time graph is velocity. And I feel like that's worth writing down because that is very important. So the slope of a position versus time graph is velocity. Now you're probably thinking, okay, Trevor, whoa. We don't even have any straight lines here, so that's cool now that you derived that the slope was velocity, but I don't even see a straight line, so how am I going to find the slope with a curved line? And if you were to take calculus, you know that means taking the derivative, but I want to argue that there is a non-calculus way to approach this, because when we go into AP Physics 1, you don't need any calculus to take this class. So even though I love calculus, you know this is a math channel, you know I love teaching calculus, let's approach this from a non-calculus approach. And what I'm simply going to say is, I'm going to say, hey, what if you just made a line, and I'm just going to do that, what if you just made a line that happened to touch that point? What if you just sprouted a line from that point? And I'm going to try and do that as best as I can. And that looks like the best I can do. So what if you just sprout a line from that point? So let me perfect this a little bit more. So now I've got this line that I've created. And what if I found the slope of that line? So we notice that the coordinates of this endpoint right here are 0.5 and 20, and the coordinates of this endpoint right here are 3.5 and 0. So to find the velocity, I'm simply just going to find the slope of the line, and of course the slope of the line is the change in your y-coordinates divided by the change in your x-coordinates. So I found that the velocity turns out to be negative 20 over 3 meters per second. That is the velocity. So what does that mean? That means that this object is traveling to the right. How do I know it's traveling to the right? Well, I know it's traveling to the right because the velocity is negative, so that means it must be traveling opposite the direction of motion. And if the direction of motion is to the left, that means the object has to be traveling to the right. So my final question regarding this position versus time graph is the cart speeding up or slowing down? So let's try to figure that out. So of course, remember, velocity is the slope. And so you're probably thinking, oh my gosh, I have to do a ton of calculations to figure out, I got to calculate tons of velocities and then compare them to figure out if the cart is speeding up or slowing down. And you're right, sort of. You're right that you have to compare the size of velocities, meaning you have to compare speeds, but you don't necessarily have to do any calculations. Here's the thing about physics, and the big thing about the AP Physics exam is that College Board is more concerned about, do you understand the science concepts compared to just being able to simply compute a math fact. So here's how I'm going to answer part C simply just by using my knowledge of science. So here we go. Let's try it without doing any calculations but arriving at the right answer. Okay, so I know that if it's speeding up or slowing down, probably gonna have something to do with velocity, and I happen to know that velocity is the slope of a position versus time graph. If I were to take a look at, say, this point right here, and I were to draw the slope right here, to draw the line at that point, and we can see that we don't have to do any calculation. We can understand that that's a pretty steep line. So if the line is pretty steep, that means it's probably going to have a very large velocity. And we could sit here and calculate it and find out that it indeed does have a very large velocity at that point. But we're not going to. We're not going to waste our time calculating because the AP exam is timed. What I'm now going to do is I'm going to draw another line. I'm going to draw it in a purple color. What if I wanted to find the velocity at, say, this point right here? Well, if I draw my line right here, and I roughly draw it all right decent, I find that this line right here, this purple line, is not so very steep. So this is the velocity of the purple line, and we've got the velocity of the orange line. And I know that since the orange line is steeper than the purple line, that means I know that the velocity of the orange line is greater than the velocity of the purple line. So what does that mean? That means that as time progresses, we're getting a smaller velocity, which means if we're getting a smaller velocity, then more likely than not, the cart is slowing down. And check that out. Just like that, you guys, I didn't have to do any math at all. I just had to look at two lines and geometrically was able to figure out if the cart was speeding up or slowing down. That's the kind of thing you should be able to do in AP Physics 1, and this was a good introduction to that, is being able to use your science practices and your scientific knowledge of physics to be able to answer these kinds of questions without having to do any math. So that's my video on the position versus time graph. In the next video, we're going to take a look at another type of graph that you can analyze in physics.